Welcome again to the Physics Online courses with Ms. Mona Shalen for grade 10 students, Dakahlia Semi School. Let's review the previous session assessment. Question number 1. A large and a small container of water with the same temperature. They will have, according to what we have discussed before, the temperature doesn't affect by the number of particles or the size of the containers, and only depends on the speed of particles or the average kinetic energy of the molecule. So it will be the average kinetic energy. Question number 2. Which row represents a correct combination of data that expresses the air pressure at seashore at night? Okay, what would happen here? Let's review the convection current. According to the fluid movement that is created by the warm fluid, here, the warm fluid, according to its density, its temperature is smaller, so it will become less dense, and it will rise up and replaced by the cold fluids, which having a higher density than the warmer air, and it be replaced and goes down, and a current circulation will be begun. This phenomena occurs at regions that are along the coastal areas, as the land has an ability to be warmer than and will be warmed up faster than water, as the water has a high specific heat capacity, which we will discuss later, and it requires a larger amount of heat to be rises 1 degree Celsius. So if we discussed at a daytime, what will happen? We call it sea breeze. At a daytime, the land becomes hotter faster than water. Cold its degree at 100 degree Fahrenheit. So the heat rises up, and this region will become a low pressure area, and then there is a cloud of hot air that rises to the cloud and undergoing a precipitation, and then comes down, and as the air above the cold waters has a high pressure, and it will form a sea breeze towards the warm land. You see here, when it's sink down, we will show it again. There is a region here of high pressures, and there is a low pressure here. Okay, in land breeze, what would happen? There is a reverse process which would happen at night. The land will be cooled down quickly, so the water will be warmer, and heat rises up, creates a region of a low pressure, and this transferred to the land with a colder land that forms, and heat sinks down, that forms a region of high pressures, that there is a current will be moved from the cooler land to the warmer water. This is a summarizing of what happened in sea and land breeze. According to day, the hot land have a low pressure, which moves the currents towards the cold waters and creates a sea breeze from the high pressures of cold waters to the hot low pressures land. During the night, the hot waters, the movement of current will be from the hot waters, which will be at a low pressures, and the current moves to the land, which will be colder at a high pressures, and that forms a land breeze. So the question here, which will be at night, the region 1 will be at a low pressure, and region 2 will be high, 3 will be low, and 4 will be at a high pressures of a colder surface. Question number 3. Which of the following previous provides a measure of the average speed of air molecules. We have discussed this in the first questions. It will be the temperature. This is the definition of temperature. Okay, let's begin our lesson for today. We will complete the second sessions we will have started for lesson 1 part 3. We will talk about black body radiation. We have discussed before convection and conduction heat transfer mechanisms, and we will talk here about the radiation heat transfer mechanism. How can we tell the temperature of the sun and the other stars across the vastness of space without visiting them? Can you ask yourself before about this question? In these sessions, we will answer this question. And also, why do the stars shine? Okay, let's classify all the surface or bodies. We have 4 types of bodies: black bodies, white, gray, opaque bodies, and transparent. The black body has a property that it will absorb electromagnetic radiations and emits electromagnetic radiations. As example for this body is sun. White bodies reflect radiation energy, not absorbs or emits, as an ovens. Gray bodies has the absorbability equals the emissivity, and the temperature of the incident radiations equal to the temperature of the body. Example of that, the metals. Opaque objects, neglectable transmissivity, and most radiation reflected and remain converted into heat. As solids and liquids, the transparent materials transfer to the entire radiation. Example of that, the dry air. Okay, we will talk in details for black body objects that absorbs and emits radiations. Only doesn't reflect radiations but emits and absorbing all the radiations incident on it. How it will occur? Black body radiations, we call it cavity radiations. The mechanism of forming a black body. The physicists study the black body by observing a hollow object with a small opening as shown in this diagram. A black body is a perfect radiator and absorber and emits radiation based only on its temperature. It is the only factor that affects on all black bodies. Okay, what would happen? Light enters from this opening according to this small opening and strikes the entire wall. Some of the energy absorbed and the others are reflected. Okay, after many reflections, all the incoming energy will be absorbed inside the cavity wall. Okay, examples for that: heat leakage from furnaces, chambers, space applications in rockets, solar energy incident on Earth, heat liberation during nuclear explosion. As the energy incident from sun to the earth, part of this energy of the electromagnetic radiation that is incident will be absorbed. 45% will be absorbed and 45 will be reflected. 45% will be reflected. Doesn't reach to the earth. If I asked you, is a shining bulb can be considered a black body or not? Can you think of that? Yes, it can be considered white hot filament to be white hot filament of the bulb considered as a good black body, as all lights from the filament is thermal radiations and most of it not reflected from other sources. It is radiated all this thermal energy. Okay, not absorbed it or reflected it or not reflected it from other sources. Other examples for black bodies: the human body, it reflects radiations, radiations in the infrared region. It is not visible, and the magma, and any hot objects that has a temperature. Okay. The characteristics of a black body. What are these characteristics? Number one, the radiated energy can be considered to be produced by standing waves. What are the standing waves? That are the waves that incident and reflected on itself and has the same amplitude with the same amplitude reflected with the same amplitude and the same wavelength. Okay, and this what happened in the black body incident rays. Number two, a black body absorbs all the incoming light of the electromagnetic radiation or any electromagnetic radiations and convert this light radiation light energy into thermal energy, which will be applied in solar heat collector. We will discuss this in the last topics or last concepts. Other characteristics is that the perfect black body at room temperature, which about 300 Kelvin, absorbs, it appears black to us. It's not a real black body, not a real black, but we haven't seen it by the naked eye. Okay, as it looks, it found in the infrared region. Most stars don't look black because most of the radiation they emit is in the range of our eyes detects. We see the star, the sun shining, not seeing it as a black body and not a black in color, but as we see the radiations emitted from them by our naked eye. Okay, the electromagnetic spectrum forms from these regions. I collected them in this statement. Read monkeys in vans used X-ray glasses, radio waves, microwave, infrared, visible lights, ultraviolet, X-rays, and finally the gamma rays. Here in the gamma rays, where the regions, in this region there is a shorter wavelength, and the electromagnetic radiation in this region has a higher energy and a higher frequency. As the energy equal h mu, so h Planck's constant, mu is the frequency. So there is a direct relation between the energy of the photon of light and the photon of the electromagnetic radiation and the energy and the frequency. Energy and frequency in these regions, in the radio waves, towards the radio waves, they will have a lower energy and lower frequency for longer wavelengths. Okay. The spectrum produced from different black bodies, we'll discuss it, by varying objects, black body objects, due to changes of its temperatures, we will the spectrum produced. Here the sun, intensity for sun, which its temperature is about 5800 Kelvin. This is a spectrum produced. Compare it with a light spectrum produced from a light bulb, which its temperature is lower than that of the sun. It will be 2950 Kelvin. Compare it with the spectrum produced from the Earth, which is about 200 degree Kelvin. The spectrum produced will be as shown. Okay, let's analyze the graph. Here is the relation between the wavelengths and density or intensity of the radiation produced. According to this graph, we will deduce that by increasing the temperature of the objects, the maximum intensity of the spectrum produced from the object will be increased, and by decreasing the temperature, the intensity will be decreased Okay, what would happen to the wavelengths? By decreasing the temperature, the wavelengths will be increased, as here for the sun, which has a larger temperature, it will have a smaller wavelength than other objects. Okay, so from the graph, you can conclude that the higher the temperature, the more the emission and shorter average wavelengths produced. Little power radiations at very low wavelengths. Here, very low wavelengths, there is a little power produced. The power radiation increases rapidly with increasing the wavelengths. For small values, the power radiation is most intense at a certain wavelength lambda maximum. Here is the value of the lambda maximum, whereas there is a maximum intensity of for the radiations. Lambda maximum increases linearly with increasing temperature. Here is the point of lambda maximum for the first body. Here is the second, third, fourth, and fifth. It will be increased. We will discuss some laws of radiations, the Planck's laws, Wien's law, Stefan-Boltzmann law, and the Kirchhoff law. We will not discuss Planck's law as well as you will discuss it in quantum mechanics, and it not you will not yet discussed yet, study it yet. So we will talk about Wien's law and Stefan-Boltzmann law. Wien's law, according to Wien's law, the peak wavelength is inversely proportional to its temperature in Kelvin. That anything that emits any amount of radiations, it has a peak wavelength. Wien's law is the equation to be used for has lambda maximum equals, this is the constant, equal 0.0029 kilometer for the temperature, over the temperature. Here is the spectrum reduced according to Wien's law for 3 different stars of 3 different temperatures. According to the wavelengths produced, the visible spectrum of lambda maximum changes for the 3 stars, and so they will have 3 different colors. Okay, here the region where the visible lights found of the spectrum, here at this wavelength. So the color of the star will be produced according to the region when its lambda maximum occurs at any regions of the visible light spectrum. Okay, why the sun appears to our eyes as yellow light, and what happened when you started heating up a piece of metal or a rock? We see that is the metal, but when we hit it, it will be glowed. Okay, what causes the different colors seen in these flames? According to the scale of temperature, there is a variations of different sources of black bodies, or that emits which has a temperature that emits different colors of different wavelengths of lambda maximum. As we heated an object, its color changes from red to orange and to white hot. You can use this to calculate the temperature of the stars from these relations. When substituting by lambda maximum for the sun, here lambda maximum that corresponds to the wavelength of the visible light, we found that its temperature will be about 5800 degree Kelvin. Okay, for other stars we can apply this to obtain the temperature of this star or the temperature of any black body object. The second law is called Stefan-Boltzmann law. It's a statement that the total radiant heat energy emitted from a surface is directly proportional to the force power of its absolute temperature. So, according to these relations, what would you expect when heating a small amount of fires and heating a big fires, the amount of energy emitted by a black body depends only on its temperature. Of course, if they have the same temperature, what will happen to the amount or total power radiated from different objects that they have the same temperature? Of course, the area that affects this power dissipated, that a burner burning a larger objects produces more energy, according to Stefan-Boltzmann law. The relation E equals sigma T bar 4. Sigma is the Stefan-Boltzmann constant. Its value is 5.67 times 10 power negative 8 watt per meter square Kelvin bar 4. Okay. There is an value called emissivity. It's equal to the ratio of the emissive power of the real body to its of the black body. Okay, its value will be obtained. It will be from 0 to 1. According to these factors, we will add it to the Stefan-Boltzmann relations. ZB over A, or power dissipated per unit area, equals sigma times epsilon, which is the emissivity, or E, times T bar 4. Okay. The value of E, or emissivity, varies according to the type of the object. Okay, if the surface would be black surface, this value will be close to 1, and the value of the power dissipated will be very large. If we replace that by a shiny metals, it will be close to 0, and thus the emitted less radiations, and we will obtain it in the materials that we want to be radiated less, to maintain it hotter, as we put the liquids that we make it to be for larger times hotter in materials that are shiny metals. Okay. If the hot object is radiating energy to another object or another surrounding of a cooler surrounding, the temperature Tc, there is a difference between temperatures that we will add a factor that delta T, or the change between the final temperature or the temperature of the hot object minus the temperature of the cold surrounding. Okay. Now, why light chiral clothing is usually preferable to dark clothing on a hot day, as they absorb a little amount of radiation that falls upon them. Most of them are reflected, and the black and dark object or clothes are good emitters, so they will be a good absorber. So the good observer are also a good emitter. Okay. Radiation emitted from the sun. The sun emits radiations by a value, emits energy by a value 1350 joules. That extracts the atmospheres of the Earth per second per square meter of area at right angles to the sun. We call this solar constant. But if the radiation of the sun is incident by an angle theta, so we will analyze the area to a cosine theta, and the value of Stefan-Boltzmann relation will become Q over T equal 1000, which the released as some 70% of the energy of the sun has been absorbed by the atmosphere, and the rest of the intensity of the incident rays will be 1000 watt per meter squares that reaches the Earth's surface. So we will multiply this by a cosine theta. Okay, we go to the natural sources of heat. The first one is the sun, and the second is the geothermal energy. The sun is a major external source of heat energy. Its energy travels to the Earth as electromagnetic radiations, and the amount of these radiations depends on the time of the day and season, but it is constantly enough as to be stored. Geothermal energy comes from the Earth's core. As this heat produced in the Earth's core is much be larger than the energy of the sun. It is produced from the molten lava, and the energy produced by a radioactive decay of the particles of rocks creating the magma. Let's see how geothermal energy works. Water in underground reservoirs heated by magma, and then this fluid flows through the walls of the surface here. It becomes heated. This water becomes heated. Its amount is very small, so it forms a steam, and that passes to the small lines, and this and reduce most of the fluids evaporates and produce a steam of high pressure. This steam then sends to turbines. To these turbines will spin a generators and generate and produce electricity. Okay, as you see here, the part of the fluid that is not evaporated will begin to return back and form and then heated, and the cycle will be repeated. Now we will see different applications of the geothermal energy. Number one is the dry steam geothermal. How it works. It's the same as we watched. There is a large pipe that contains the fluids. This fluids flows heated and then flows through a pipes and then rotates the turbines to generate electricity. The second type is called the binary cycle geothermal. Binary, it uses two types of fluids. Here is the hot fluids from the underground that is heated. The second fluid, which is a colder fluid and has a slower boiling point than the other. So there is a heat transfer. There is a heat transfer here between the two fluids. Called it a heat exchanger, which joins the hot water with the fresh water, and so on. It rotates the turbines and rises the which rides the turbines and generate electricity. Another application of the geothermal energy is the cooling effect of the geothermal heat energy. You will see here it requires a heat solar heat below the underground by 5 feet, by underground the earth's surface by 5 feet. It happens here. There is two types of pipes. One contain a hotter one and the other contain a cooler liquid. Water enters into the circulations. Here is the compositions of the heat pump and how it works. It has two main parts: the exchange valve, the expansion valve, and the compressor. There is two phases: gas and liquid. Refrigeration works that by raising the pressures and temperature will be rises. This is a concept here that we have studied before in fluids. by increasing the pressure, its temperature will be increased, which is the rule of the compression. Okay, here is underground water, which circulates to the compressor, and then the compressor increases its temperatures and by increasing its pressure. You will see. Watch the circulation here. Water comes by 30 degrees. The fluid evaporated, and then the compressor raises the temperature of the gas, and here it comes here as a steam. And this is the rule of the compressors. Increases its temperature from 30 to 160 degrees, and then it passes across a fan, which cools it down, and some of the heat will be absorbed by the heat energy absorbed during the container, and the temperature will be decreased and it becomes 85 degrees, and then it comes to a region is a small hole which has a smaller cross section area, so it will have a small pressure, so if the water will the expansion valve will convert the gas here to a liquid again. Okay, and will be cooled down as it will be condensed the gas flow into a water again, and its temperature will be 20 degrees, and so the cycle will be circulates again. Let's see what is the solar heat collector. It collects the heat by absorbing sunlight. Collectors, it's a device that captures solar radiations. Solar radiations that we have discussed before, the infrared regions, from the infrared regions and visible light to the ultraviolet region. So how solar heat collector works? Solar heat collector consists of 6 parts. The first one called the solar collectors. Here is the pump station, and then the hot expansion tank, differential collector, storage tank, and finally the backup heater, which is the tank. Energy from the sun is transferred to the glass of the collectors and absorbed to the materials of this glass. It acts to absorb all the radiation that incident on it and converts it into heat. Then the heat energy produced will be passed through these pipes, which have a small cross-section area. This is the absorber plate. The gas will be circulated here across the pipes, and then reaches the heat exchanger here. To reach its temperature will be maximum temperature. Then the controller here will be stopped until the tank temperature drops again and the cycle continues. Okay, as it absorbed more energy and store it for another use. We can use it in different applications, as in shower bath. Here we store it using a storage for the heat energy. Also, we can circulate it into the fossil fuels and another application.